Hello, everyone. I'm Fiodar, and today I'll be talking with Deepak about POP, a method to solve large-scale resource allocation problems efficiently. This is joint work with collaborators at Stanford and Microsoft Research. In today's large systems, resource allocation plays an important role in overall system efficiency. Resource managers allocate system resources, for example, servers in a data center, to clients or users of the system, with an objective in mind, whether it's fairness among clients or maximizing the global utilization of the system. And it outputs an allocation, which maps clients to resources in the system. This abstraction applies not just to cluster scheduling, but to other systems as well. Clients can be commodities in a network where we allocate link bandwidth in order to maximize the total amount of flow, for example. The allocation might be recomputed every few seconds or every hour, depending on the temporal properties of the clients using the system. As a concrete example of a resource allocation problem, let's consider the assignment of servers to users with a simple utility maximization objective. Utility in this case encodes the preference of user I to server J. An example could be the cost to run the job on a particular cloud instance. This resource allocation problem is an integer linear program, shown here on the left, and we can try to solve it in a couple of different ways. For example, we could directly use a modern state-of-the-art solver like Mosaic. This would take a long time to run, several hours for thousands of users and resources. Or we could devise a heuristic, such as a greedy algorithm, to try and solve this problem. This could do okay, but might also get stuck in a local maxima and never find the true optimal solution. In this talk, we propose a new technique called partitioned optimization problems, or POP. We identified a new class of resource allocation problems, which we call granular, and found that many optimization problems in existing systems belong to this class. We can solve granular problems quickly with POP. A distinguishing feature is POP's simplicity. We take the system, randomly partition it, solve the optimization problem on each partition, then coalesce the results into our final allocation. We'll also show how many problems that are not granular can be easily transformed into granular problems, on which POP can be applied. Our evaluation with POP shows several orders of magnitude faster runtime for computing near optimal solutions. The rest of this talk is organized as follows. We first characterize a class of optimization problems that occur in large systems. We then describe how to POP these problems and evaluate on several different systems and objectives. Our key insight is that a number of allocation problems across domains, cluster scheduling, traffic engineering, load balancing, and databases, these have several properties in common. The first is scale. Systems can have hundreds or even hundreds of thousands of clients and resources. This is partly what makes these problems hard in the first place. The second is that clients are small. This often goes hand in hand with scale, and each client can use only a small fraction of the available resources. The third condition is fungibility. For every client, there are many resource instances on which they get similar utility. For example, a GPU cluster will have many identical GPUs, and a client doesn't prefer one over another. POP exploits these conditions to quickly compute good allocations. Let's look at examples of granular problems. In real systems, the server assignment problem I mentioned earlier is granular. When the system is large, there are many users and servers. Each user requests a small fraction of available servers, and we typically see many instances of each server architecture in the resource pool. Here's a more complex example from a research system published in 2020, featuring a GPU cluster with several types of GPUs. The allocation objective is standard max-min fairness. Maximize the minimum normalized throughput of any job in the cluster. What we want to compute is an allocation matrix A, where AJI specifies the fraction of time a job J spends on resource I. In large GPU clusters, this problem is granular. We have a large number of jobs, no job is too big, and there's a large amount of each GPU type. Next, Deepak will describe how POP operates on these granular problems.
Thanks, Fiodar. I'll illustrate how the POP method works for the server assignment problem from before, at the level of both the system as well as the optimization problem. With POP, we start with a large system with n clients and m resources and split into k subsystems, where each subsystem has an equal share of clients and resources. Remember that our original formulation modeled the allocation for this problem as an n by m matrix of variables. With POP instead, each subproblem is responsible for a subset of the clients and servers in the original problem. In a particular example, each subproblem has a smaller allocation matrix of size n over k times m over k. POP is able to achieve runtime speedups of the full problem formulation since runtimes of solvers scale superlinearly with the number of variables, and subproblems can even be solved in parallel. The main reason we can only apply POP to granular problems is because our method reduces the search space that solvers consider. We need granularity to ensure that the solver is able to consider enough high-quality feasible allocations. For example, client resource fungibility ensures that every client has at least some resource that it has high affinity for in the same subproblem. We can do something very similar for the fair sharing policies expressed using the Agrawal framework from OSTI 2020. In particular, we randomly partition jobs and GPUs of different types in the subproblems, and then reuse the original solver and problem formulation for each subproblem. Finally, we concat the individual allocations from each subproblem. Unfortunately, not all resource allocation problems are granular. For example, it is easy to imagine clients with large demands, thus violating condition 2 of granularity. Similarly, many systems can also have rare or unique resources, violating the fungibility condition. One specific case of problems where these violations can manifest themselves is in traffic engineering, where every link between two sites is a unique resource. Specifically, let us consider a simple max flow traffic engineering problem where we try to allocate link capacity to various commodities while respecting and trying to get as close to each commodity's demand. This problem can have some commodities with high demands and might also require the use of links between specific sites to ensure a high total flow. In such cases, we can apply client and resource splitting transformations to transform such non-granular problems into granular ones. Let us now see how POP does in practice. We evaluated POP on 3 different domains: DNN cluster scheduling, using the same problem formulations from the Agrawal research system which appeared at OSTI this past year; traffic engineering using the problem formulations from the NC-Flow research system which appeared at NSTI earlier this year; and load balancing for a distributed database. To evaluate POP's generalizability, we tested it on different objectives. For example, for the cluster scheduling domain, we looked at 3 different objectives: maximum fairness, proportional fairness, and minimize makespan. For the traffic engineering domain, we looked at 2 objectives: total flow and maximum concurrent flow. Our method shows extremely good results in practice. For example, with a maximum fairness objective for GPU cluster scheduling, we can produce a 23x speedup in runtime with little drop in accuracy compared to using the full problem formulation. Note the logarithmic scale on the x-axis. POP k uses k subproblems, and we observed that the speedup increases with k. We can also improve allocation quality by up to 1.9x compared to heuristics like those employed by the Gandiva scheduler. This is for a static workload, but we see similar order of magnitude speedups when using POP with Agrawal simulator, with little change in relevant end-to-end metrics like average job completion time. POP also performs well for various traffic engineering objectives. For the total flow objective on a topology with 754 nodes and 1790 edges and 500,000 commodities, POP with 64 subproblems is up to 131x faster than using the full problem formulation, while retaining almost entirely the same flow. We can also apply POP to maximum concurrent flow, which is a fairness objective for traffic engineering. POP can decrease runtimes from hours to tens of seconds. Thus, we see that POP results in faster runtimes with almost identical allocation quality across objectives. To conclude, we observe that many real allocation problems are granular and can be accelerated using a method we call POP. We observe that randomly partitioning clients and resources into subproblems and simple greedy client and resource splitting algorithms work well in practice. A key takeaway is that one shouldn't give up on large optimization problem formulations for resource allocation or quickly fall back to heuristics. Instead, POP is a viable method to produce high-quality allocations efficiently. Our code is open source on GitHub, and with that, I'm happy to take questions. Thanks for listening.